Hello, my name is Mishaal. Today my topic is about what is CPU cache and why does it matter from my computer architecture class. I'll begin by explaining what the CPU cache is. The CPU cache is a small high-speed memory that stores the most frequently accessed data and instructions. It is built into the CPU directly, making it faster than machine's RAM. By keeping the important information or recently used data close to the CPU, the cache will reduce waiting time for the CPU, improving the overall performance. This image shows how the CPU interacts with the cache and RAM. The cache is sitting between the main memory and CPU, giving faster access to recently used or accessed data, speeding the performance of the machine up. Moving on to bottleneck and memory. Now that we know what the cache is, let's understand why it's so important. Modern CPUs can perform billions of operations per second, but main memory or RAM is much slower in comparison. This creates a bottleneck. Think of it as a race car that has to slow down every time it needs to refuel from a distant pit stop. The CPU ends up sitting idle, waiting for the data to arrive from the RAM. That's where this cache comes in by storing frequently used data closer to the CPU. It helps avoid delays and keeps the processor running at full speed. Imagine having like a jerry can for your gas in your back trunk. The image on the right shows this clearly. We move from the CPU's register down to L1, L2, and the L3 cache, and finally to the RAM and storage, latency increasing dramatically. This is the bottleneck, and the cache helps reduce it by storing frequently used data closer to the CPU. In the image on the left, you can see how the CPU has to wait for data to travel from RAM through to memory controller. This delay is what we call memory bottleneck, and is exactly what the cache is designed to reduce. Now we discuss locality. Locality, which explains why the cache is such a useful tool. There are two main types, temporal locality and spatial locality. Temporal locality means that the CPU recently accessed some data, it is likely to need it again soon. A great example of this is when a player repeatedly opens the same character menu in a game, and the system remembers that and loads faster the next time. This is clearly shown on the image on the left, which is a character menu that gets repeatedly opened for a user. Spatial locality means that it's a piece of memory that's accessed, and then nearby data of that piece of memory that was already accessed will probably be accessed next. In gaming, when you're playing or exploring the world or doing any type of activity, the environment like hills, sand, lighting effects is often loaded in nearby chunks. That's what you see in the image on the right. The cache takes advantage of both types of locality by keeping frequently or nearby used data ready, speeding up the performance significantly and providing a smoother and better experience overall. Notice how the first time you load into a map or the boss right here is slow? This game pulls all that data from storage, usually an SSD or even slower, a hard drive, and places it into the RAM or cache if you do a second attempt or loading again, and that's why it takes longer the first time. As you see during the gameplay, there's a lot of things being cached, like the character's models, terrain assets, as you see in the background, there's like curtains, chairs, tables, carpets, and all that. Those are also being cached because those are frequently accessed. Menus like my weapon or my healing ability or my health bar, stuff like that, is also being cached because it's frequently used. Sounds, lightings. This is an example of how it's used in everyday life. You can see how the first load was slow and the second load was faster. You can also see both locality types in this, showing temporal locality where my weapon skill being used over again, or my menus popping up when I pop a consumable, stuff like that. Or spatial locality, which is running across the field while fighting. You can see all the stuff loading, all the sounds, and everything's loading together. Now we will discuss how a cache is used in CPU. When the CPU loads data into the cache, it needs a strategy to decide where each block of memory should go. The process is called cache mapping, and there are three main methods. The first is direct mapping. In this method, each memory block is assigned to exactly one spot in the cache. It's fast, but if two blocks compete for the same location, it can cause frequent conflicts and cache misses. Next is fully associative mapping, where any memory block can go anywhere in the cache. That gives it the most flexibility and reduces conflicts, but it is slower to search since the CPU may have to check every cache line. In the middle, we have set associative mapping. This is the most common in real-life CPUs. Each memory block can go into one of few spots in the set. This offers a good balance between speed and flexibility, fewer conflicts than direct mapping, but faster lookup than the fully associative one. Now we'll discuss full cache issues. When a cache is full and new data needs to be loaded, the CPU has to decide which existing block to remove to make space for the new data. This is where cache replacement systems or replacement policies come in. They determine what gets evicted to make space. One of the most common is LRU, or least recently used. It removes the data that hasn't been used in the longest time under the assumption that it's least likely to be used again. Another is FIFO, or first in, first out. This removes the oldest block in the cache, regardless of how often it has been used. It's simple, but not always optimal though. Another is random emplacement. It chooses a block to randomly evict. It is easy to implement, but may remove useful data. And finally, we have pseudo LRU. This is a hardware friendly alternative to the true LRU discussed previously. It approximates recency tracking with far less complexity, and it's commonly used in real processors like Intel's Alder Lake chip or Intel CPUs. Now we'll discuss real CPUs with cache. Let's look at how cache is used in the real CPUs that we use today. The Intel Core i7 12700K, for example, includes the 32 kilobytes of L1 cache per core, a 1.25 megabytes of L2 cache per performance core, and a shared 25 megabytes of L3 cache across all the cores. That gives each core access to fast local cache while also benefiting from a shared larger pool. On the other hand, the AMD side, the Ryzen 7 5800X, the similar structure with a 64 kilobytes of L1 per core and 512 kilobytes of L2 per core and 32 megabytes of shared L3 cache across the whole chipset. This gives Ryzen strong cache performance for gaming and productivity. Also, the patent, but it's not just about the size, modern CPUs also optimize how cache is shared and allocated dynamically. In 2019, Intel filed a patent, shown below, for a system that adjusts cache distribution across CPU cores based on the workload. This allows high demand cores to use more cache space, improving speed and efficiency. Next, we have cache innovation. As processors have evolved, so have the strategies used to manage cache more efficiently. Beyond just sizing and mapping, innovation in replacement policies and cache control plays a major role in modern CPU performance. One example of this is the pseudo LRU, a technique used in high associativity caches. In a 2012 study, peer-reviewed study, Jamez introduced a tree-based pseudo LRU system that mimics true LRU performance but uses much less hardware. This approach is now commonly used in real CPUs like Intel, offering a strong balance between speed and efficiency. Another innovation is ARC, or Adaptive Replacement Cache, introduced by Megiddo and Modha in 2003. ARC automatically balances between recently and frequently used data, making it highly adaptable to different workloads. It outperforms both LRU and LFU in many real-world scenarios. We also see innovation in how cache is dynamically managed, as mentioned earlier in Intel's 2019 patent. It describes a system that monitors core activity and reallocates cache in real time. This ensures high priority cores get more cache space, boosting multitasking performance. Next, we'll talk about why cache matters. To wrap it all up, cache is a small part of the CPU, but it plays a huge role in the performance of the CPU. It bridges the speed gap between CPU and RAM, reducing how often the processor has to wait for data. The cache hierarchy L1, L2, and L3 keeps the most useful data close, enabling a faster execution. Principles like temporal and spatial locality help the cache predict what the CPU will need next. When the prediction is correct, and you will get a cache hit, everything runs faster. Behind the scenes, mapping strategies and replacement policy decide how the data moves through the cache. And in real CPUs like the ones from Intel and AMD, advanced techniques like dynamic cache allocation and pseudo LRU help keep things effective. So even though cache is just a small piece of silicon, it is one of the biggest reasons that modern CPUs are fast and powerful as they are. These sources will be posted in the description of this video. Here are all my sources for the images and information I used. These sources include online articles, peer-reviewed journals, and more, but excludes in-class lectures and slideshows. I hope you enjoyed my presentation, and I look forward to seeing the others.